And we're back and better than ever, still in 17.1, where we're dealing with the flow of heat. In the first podcast of this chapter, we introduced you to the idea of heat in thermochemistry. We talked about the fact how heat always flows from warmer objects to cooler objects. How when we're analyzing our objects, we break the universe down into two parts, the system and the surroundings. When the system absorbs heat, it's called an endothermic process. When it releases heat, it's called an exothermic process. And of course, energy is conserved in any process. And we wrapped up the last podcast talking about the different units that we'll be using to measure heat and heat flow. Now what we want to talk about is how different objects will absorb various amounts of heat and change in temperatures by varying amounts. And that's a topic that really starts with heat capacity, which is simply the amount of heat needed to increase the temperature of an object by 1 degree Celsius. So any particular object can be given or assigned a heat capacity, or you can actually measure it by material on a per gram basis. For example, if you took a look at, say, a pop can, an aluminum can, you could actually measure the heat capacity for that particular aluminum can. But it would be different if you're using an aluminum, say, jumbo jet. Even though they're both made out of aluminum, the jumbo jet is a whole lot bigger, so it can absorb a whole lot more energy. So oftentimes, rather than dealing with heat capacity, we deal with the specific heat of a particular material. And the specific heat is on a per gram basis. Okay? Now there's an equation that we typically use when we're using specific heat, which is Q equals Sm delta T, where this measures, the Q is obviously the heat, the delta T is the temperature, the M is the mass of the object, and the S is going to be the specific heat. All right. I've also seen it written H equals Cp M delta T, where again H is the heat. It actually stands for the enthalpy. We'll get to that later on in this chapter. Cp is going to be the specific heat, and then M is the mass, and the delta T is the same. Or you could have a combination of all those variables between the two equations. Bottom line is we want to be able to use this type of equation to measure the temperature change when a certain amount of heat is added, or vice versa. If we measure the temperature change, we should be able to calculate the amount of heat that was actually transferred. Now in terms of specific heats, here are various specific heats of different objects. First of all, you're going to notice that metals tend to have very low specific heats, which means that they heat up very quickly. If you have a low specific heat, it takes very little heat to raise the temperature of that object. Well, metals will heat up very quickly. They also cool down very quickly. On the other hand, nonmetals, including other compounds like water, are going to tend to have higher specific heats. And in fact, water has a tremendously high specific heat, especially for the size of the molecule. All right. So let's go ahead and perform some of these calculations and see how these things work. So, sample 17.1. The temperature of a 95.4, that should say gram, piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when the copper absorbs 849 joules of heat. What is the specific heat of the copper? All right. So if we use our equation Q equals Sm delta T, we're actually looking for the specific heat, S. So let's go ahead and solve for that first, and then we'll plug in our values. So we're going to divide both the mass and the change in temperature over to the other side. Of course, these terms will divide out with these terms, and our specific heat S will equal the heat Q divided by the mass and the change in temperature. The heat change was 849 joules. The mass of the object was 95.4 grams. And the change in temperature, well, any change in temperature is going to be the final minus the initial temperatures. So the final temperature was 48 degrees Celsius. The initial temperature was 25 degrees Celsius. Notice none of the units have divided out. That'll be something we'll address in just a second. So we have 849 divided by 95.4, and then again divided by the change in temperature, which is actually a total of 23 degrees Celsius. And it looks like we get a specific heat of 0.387. And the units on that are going to be joules per gram per degree Celsius. Just like the units that were given above for the specific heat, where you have joules per gram per degree Celsius right here. Alright, so that is the specific heat of copper. And notice that is a reasonable value, because when you compare that to other metals, they tend to have fairly low specific heats, and copper does. Alright, let's go ahead and try a few more problems. When 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temperature increases to 85. What is the specific heat of the olive oil? Let's go ahead and try this one again. Same setup. Q equals SM delta T. I'm going to divide the M and the delta T over to the other side, so that those terms divide out here. We isolate our variable S, which we're looking for. So the specific heat will equal the heat transferred divided by the mass and the change in temperature. The heat was 435 joules. The mass was 3.4 grams. The temperature change was, well, it started at 21 and ended at 85, so it's going to be 85 minus the 21 degrees Celsius. And so therefore the 435 divided by 3.4, and then also divided by the change in the temperature, which is a total of, this is actually a total of 64 degrees, isn't it? It looks like we got a specific heat of 2.00 joules per gram per degree Celsius. And notice it's much higher than the metal, which would tend to have the lower specific heat. Alright. Let's try one more. How much heat is required to raise the temperature of 250 grams of mercury at 52 degrees Celsius? And we actually need a final temperature here. So let's say that it's going to be starting at room temperature. We'll say that it's starting at 25 degrees Celsius and it's going to go up to 52 degrees Celsius. How's that? So we have our Q equals SM delta T. The question is looking for heat. It says how much heat is required, so we're looking for that. So now we need to know the specific heat of the mercury. Well, if you scroll up to the table, mercury, which is on the bottom, has a specific heat of 0.14 joules per gram per degree Celsius. So we have 0.14 joules per gram per degree Celsius. The mass is 250 grams. And the change in temperature is going to be the 52 degrees Celsius minus the 25 degrees Celsius. And now notice that first of all the grams divide out top and bottom. The degrees Celsius also divides out top and bottom. And so therefore 0.14 times 250 times the change in temperature, which appears to be, what, 27? If you take 52 minus the 25, that would be 27 degrees Celsius. So let's multiply that by the 27. And it looks like it is 900 945, and the units on that will be joules. So it'll take 945 joules to raise 250 grams of mercury from 25 degrees Celsius up to 52 degrees Celsius. That takes us to the end of 17.1.